Hello everyone, I am here in spirit to teach you about the combined and ideal gas laws. These are the next two formulas that we're going to be looking on your formula sheet. Just as a quick review, we are going to look at gas properties. Hopefully you have already kind of inferred these properties from our conversations or came with this knowledge, but I think we should probably look at how gases behave in general. They do have mass. They will diffuse, meaning they will spread evenly and mix evenly in a mixture. They can expand to fill the containers. They do exert pressure due to those collisions. They are compressible because the distance between the particles is so large you can push them together and take up less volume. And then, of course, the behavior of the gas is dependent on pressure and temperature. Four variables that we've looked at so far. The first is volume. We're going to measure that in liters or milliliters. We have moles or number of particles. The unit is the mole. Just a reminder that you cannot plug in grams for moles, so you have to rely on your expertise of using the periodic table to convert those grams to moles. Temperature, which is the motion of those particles tied to the energy, we have to convert to Kelvin. That way 0 Kelvin means 0 energy. Kelvin is simply the degrees Celsius plus 273. And then finally, pressure from those collisions with the container. Many units we can look at: pascals, kilopascals, ATM, millimeters of mercury, or torr. So far we have actually looked at four separate gas laws. The first two deal with volume. Boyle's law deals with pressure and volume. Inverse relationship between those. As you increase the pressure, you're going to decrease the volume. Avogadro's deals with moles and volume. This is a direct relationship. As you increase the mole, you increase the volume. Gives us two different formulas: P1V1 equals P2V2 and N1V2 equals N2V1. The other two laws, a little more review. The other two laws are Charles's law and Gay-Lussac's. These are going to deal with temperature. Temperature and volume, again, a direct relationship. As you increase temperature, you increase volume. Hopefully, with our discussion of the kinetic molecular theory yesterday, you realize because at a higher temperature, the particles are moving faster. That allows them to expand and take up a larger volume. Gay-Lussac's law is going to deal with temperature and pressure. Again, a direct relationship. And again, looking at the kinetic molecular theory, as the particles are moving faster, they collide more with the sides of the container. And with greater force, which increases that pressure. Again, two laws, two formulas that we have for those laws. T1V2 equals T2V1 and T1P2 equals T2P1. Now, what if we were able to, if we only kept the moles constant? Remember, in those prior laws, you have to hold two of your variables constant. What if we decided to only hold moles constant? This could be very useful to us because that way we could change more than just one variable. Well, we actually do that in the combined gas law, which is P1V1 T2 equals P2 V2 T1. Convince yourself while looking at this formula that you can see Boyle's law in there, you can see Charles's law in there, and you can see Gay-Lussac's law in there. The only law that is not included is Avogadro's law, which is why we have to keep the number of particles constant. Let's look at an example using this combined gas law. Right, a balloon holding 2 liters of air at 20 degrees Celsius and 1 atm of pressure rises to a height of 1,600 meters above the Earth. The temperature there would be 10 degrees Celsius and the pressure would be 0.17 atm. What would the volume of the balloon be? You can see that this is a combined gas law problem because we are changing both the temperature, which is decreasing, and we are also decreasing the pressure when it rises in the atmosphere. So because we're changing two of the variables, we are going to use the combined gas law. P1V1 T2 equals P2 V2 T1. We are looking for what the volume would be at that higher altitude, which means we are looking for V2. In order to calculate V2, we do need to know the initial pressure which when you're holding the balloon on Earth is 1 atm. The initial volume is 2 liters. When we look at the final temperature, this is after it has reached that altitude, we're at 10 degrees Celsius, which means that we are at 283 Kelvin. And then we also must know the new pressure, which is 0.17 atm when we raise to that new altitude. And then our initial temperature down on Earth was 20 degrees Celsius, which would be 293 Kelvin. We can plug in all of those variables into the formula. To solve for V2, we're going to have to divide both sides by 0.17 atm and 293 Kelvin. Hopefully you can see that the 293 Kelvin will cancel, the 0.17 atm will cancel on the side with our variable. And then on the other side, our atms and our kelvins will cancel as well. So we'll be left with just liters, which is a volume. And so we can calculate this and we get a volume of 11.3 liters. Now it will get a little more complicated when you start looking to see if this is a reasonable answer or not, because we're really changing two things, and they could contradict each other as they do in this example. Because when we lower the temperature, what do we expect the volume to do? And the answer is we expect, if we lower temperature, we expect the volume to decrease, but we are also lowering the pressure, which results in an increase in volume. So we started with a volume of a balloon that was 2 liters. We ended with a volume that is 11.3. To see if this is reasonable, we would have had to lower the pressure at a greater ratio than we raised the lowered the temperature, which is exactly what happened. So this gets a little more complicated to see if it's reasonable, but you still can check to make sure that your answer makes sense. So the combined gas law is pretty simple. It's not a lot different than what we have already been working with. That brings us to the ideal gas law. The ideal gas law will actually allow us to calculate an unknown without having to change any of the conditions, which is pretty powerful. Now you're going to see the same variables in the ideal gas law that we saw in the other formulas. You're going to have pressure, you're going to have volume, you're going to have moles, and you're going to have temperature. But what we're going to add now is a universal gas constant. So here's your formula. PV equals nRT. You can see pressure, volume, there's your moles and your temperature, and then we have that R, which is a gas constant. I affectionately call this formula PERV-NERT, which probably just made a couple of you chuckle, but I think it helps you remember the formula. So I will often not call it the ideal gas law, but call it PERV-NERT instead. Now that gas constant, we have two different gas constants that we can use. One is 0.0821, and that's liter atm per Kelvin mole, or we can use 8.31 liter per kilopascals per Kelvin mole. Hopefully you can look at this and see that the only difference between these two gas constants is that unit of pressure. But when you plug in all of your variables, the variables now have to match, the units on the variables now have to match the units that are in your gas constant. So we have to be pretty particular in those units. So if we go through the gas constants, volume has to be in liters, temperature has to be in Kelvin, your pressure has to be in kilopascals or atm, and depending on which pressure you have will determine which gas constant you use. And then you must have moles. You cannot plug in grams, you have to plug in moles. So let's look at an example of the gas law as well. A camp stove propane tank holds 3,000 grams of liquid propane, which is C3H8. How large a container would be needed to hold the same amount of propane as a gas at 25 degrees Celsius and a pressure of 303 kilopascals. Now, this is a perv-nert problem, and you can see that because we're really not changing any of our variables. Now, we are changing our states from a liquid to a gas, but we're not changing temperature, we're not changing pressure, we're not changing the moles, and we're looking for what that new volume is because we want to know how large that container will need to be to hold that same amount of volume as a gas. Well, in order to solve for V, we have to know the pressure, which is given as 303 kilopascals. We also need to know moles. Now, we're given 3,000 grams, so I had to use the periodic table to see that the mass of propane is going to be 44 grams per mole. So that tells me that I have 68.2 moles of propane. We have to pick a gas constant. I chose the 8.31 liter times kilopascals per Kelvin mole because my pressure is in kilopascals. So this way that those units are going to cancel. And then the last thing that I need is a temperature. And the temperature is 25 degrees Celsius, which is 298 Kelvin. And once I identify all my variables, I'm going to go ahead and plug those in. So there's my pressure times my volume. There's my moles, my universal gas constant, and my temperature. So how are we going to solve for the volume? We're going to do that by dividing both sides by 303 kilopascals. And hopefully you can see that the 303 kilopascals will cancel, but we have a lot of things happening to our units on the other side as well. Obviously the kilopascals are going to cancel, but you also are going to be canceling your moles, and you're going to be canceling your Kelvin, which leaves a unit of liters, which is a volume. So once I do the calculation, I will get a volume of 557 liters. Again, this isn't really complicated. The hardest part is identifying that this is an ideal gas law problem, and you're going to identify that by the fact that we are not changing any of our variables. All right, so we've learned about the combined gas law. We've learned about the ideal gas law. So of course I'm going to give you some homework that you need to work on. Use your time in the rest of class. There's Chemistry Cat there teaching you about absolute zero, and I know you guys are like, okay. Homework that you're going to be working with. You're going to get some mixed gas laws practice worksheet. That should be done. You're actually going to have a quiz over this on Tuesday, so make sure it is done by Tuesday, and please make sure you're showing your work as well, because again, if you're not getting the answers, your work is what helps me figure out where you're making your mistakes. Then you'll also be getting and analyzing the Popcorn Lab. We'll be in lab on Wednesday. This uses the ideal gas law, so make sure that pre-lab is done by Wednesday. And of course, I want you to read through the procedure and answer those pre-lab questions. It is not a formal lab write-up, but make sure you're ready for lab on Wednesday. All right, I hope everyone has a good weekend and use your time wisely. Thank you.